This is a short lesson on how we include the concept of adding or subtracting line segments in our proofs. First, I want to show you outside the context of a proof, and then we'll do a couple of examples. Let's say we have this picture here, and I know these two things. Maybe I was given them, maybe I was able to prove them using corresponding parts. But I know AB is congruent to DE, and I know BC is congruent to DC. So I've marked those congruent pairs. It's pretty clear that if these are the same and also these are the same, then we can add this length up and add this length up, and the length from A to C is going to be the same as the length from E to C, which means that AC is congruent to EC. This is the idea of adding segments. It's a little bit like adding equations, except you have to look at the picture. This wouldn't make any sense if these were bent. If I went A, B, C like this, I couldn't add these up, these segments, to get a new segment in any meaningful way. But because these line up, I can say, well, those match and these match. So if I combine this together into a longer segment, I combine these together into a longer segment, those must also match. Here's how we'll write this in our flowcharts. We'll take the two facts that we're going to add or subtract, put them together, and we'll line them up as if we were going to add equations like in Algebra 1 or Algebra 2. Notice I'm going to have AB and BC. These two here are the left pair. Then I have DE and CD. These two here are the right pair. And then I'm going to add them. I'm going to say, well, because I know this and because I know this, I can add these two congruences and get a new congruence. AB plus BC is the longer segment AC, and DE plus CD is the longer segment CE. And since I'm adding here, I'll just write addition. These would have whatever reasons that we figured out those were true. Maybe those were givens, or maybe those were something we proved. But underneath this box, we'll write addition, because that's what we're doing. We're adding this and we're adding this. So it looks a lot like adding equations from Algebra 2. You line up your congruences. You have to look at the picture to make things line up properly, and then you add AB plus BC is AC, and DE plus CD is CE, the longer one here. And so we can deduce this congruence is also true. Let's do a couple of examples where it's in proofs. So here's my first example. Let's start, as always, by marking our givens, and then we'll see where we can go with that. So angle A is congruent to angle Z. Okay, so I'll mark those angles as congruent. AB is congruent to YZ. AC is congruent to XZ. Well, that's pretty straightforward. I don't have to do anything particularly tricky here at all. I already have marked on these two triangles side, angle, side, and the corresponding set of tick marks over here. And so that means that these two triangles are congruent. And so I could just write down, okay, those triangles are congruent. But look what I want to prove. I want to prove BX is congruent to CY. So if that's B down to X is the same as C down to Y. That's actually longer than the side of the triangle. So we'll have to do something after we prove the triangle is congruent. Let me show you how it looks. So I'm going to prove, let's see, let's call this triangle BAC. I went like this, 1 to 2 tick marks. So this one would be called YZC in the corresponding order. This will be SAS, and here all three of my congruences in the SAS package are just givens. So this is pretty straightforward. I have angle A congruent to angle Z. That's a given. AB is congruent to YZ. That's a given. And AC is congruent to XZ. That's a given. So, but where do we go with this? I want to show B, look at what I'm trying to prove. B to X is the same as C to Y. So B to X is not a side of either triangle. It's longer. It includes BC, but it's longer by CX. So when you're trying to prove something and what you know is too short, because we know, let me take a step back here, we know because of this congruence that BC now is going to be congruent to XY. Those are corresponding parts of these now congruent triangles. We've shown that these triangles must be exactly the same shape and size. So that means BC has to be the same as XY. And so when something is too short, like here, I don't want BC, I want BX, it makes sense. If something is too short, I'm going to look to add. So here, to grow BC into BX, I would need to add CX here in the middle. And in the similar way, to grow YX into YC, I would need to add the same segment here in the middle. So this is how it's going to work. So let me show you how we write it up. From the triangles being congruent, I can conclude BC is congruent to XY. That's corresponding parts. I'm writing this on the side because I'm getting ready to do my addition. So that was BC congruent to XY. And then I want to add to each of those the segment in between, CX. I want to add to BC, CX, and I want to add to XY, CX. So I'm going to take BC, I'm going to add CX to it. I'm going to take XY, and I'm going to add CX to it also. This needs a reason also. We can't put something down unless I have a reason for it. Of course, here, this is obviously just the same segment, or if you prefer, you can write reflexive property. But it's important that each of these has a reason. This will prevent you from simply writing down what I call wishful thinking, where you'd like to add, and so you just say, well, if I add this, I'll get what I want. But if you don't have a reason for both of these statements, then your logic isn't solid. But here I do. BC congruent to XY are corresponding parts, CX congruent to CX are the same segment. So when I add, if I look back at the picture, BC and CX, that gives me BX. And XY and CX gives me C to Y. And this will be right under here, we are adding addition. And so this is how we use adding in proofs. Let's do one more example where we have to subtract. So let's start as usual with marking my givens. BX congruent to DX, okay. And then I have this kind of annoying BC congruent to DA. And that's kind of hard to mark because if I put tick marks on here, it might make me think that CX is what's matching something. So I do kind of this awkward bracket along here and put a double tick mark on it. Say, okay, from there to there, and then likewise, I'll draw this bracket and do there to there. It's kind of messy. The tick marks eventually begin to break down in really complicated diagrams, but you're just trying to show yourself the information. It's a visual reminder. I want to prove angle B is congruent to angle D. So clearly, if I could show these two triangles congruent, then angle B and angle D will in fact be congruent angles. Now, we have to remember that we do have this X shape. So I can say these here are vertical angles. And it looks like, if you're not careful, that you have side angle side. But this tick mark is too long. A to D is not a side of either triangle. It goes across both. You have to have sides and angles of triangles going into your SAS. Let me say that again. It must be exactly a side or exactly an angle of the triangles. If something is too long, it won't work. You're going to have to subtract to make it the right length. If something is too short, it won't work. You're going to have to add. So here, I have A to D, which is too long, and B to C, which is too long. What I would like is I would like this. If you look buried in this diagram now, I have an angle side angle. This is an X here, the letter X. I have an angle, or it's not, pardon me, we have a side angle side pattern here, and then we have the similar side angle side pattern here. B to C is too long, I need to make it shorter by removing bx. A to D is too long. I need to make it shorter by removing dx. Now we'll shrink it down to the sides that we need. Then I'll have side, angle, side. Let's look at how this looks when we write it up. So I'm going to have bx congruent to dx. That's a given. Then I have these angles in the middle. Angle BXA is congruent to angle DXC. Those are vertical angles. And then last of all, I want AX congruent to XC. I'm going to put it down a little bit. You'll see why in a second. But that's not a given. This is part of my side, angle, side, side, angle, side. This is not a given, though. I have to get it by subtracting. So let's look at how am I going to produce AX? Well, I'm going to get AX by taking AD and subtracting DX. So you get AD, DX. I'm going to subtract these. And then on the other side, these are always going to be congruences. Notice my subtraction is lined up this way. Don't do this. This is just going to confuse you if you write subtraction like this. This is not the way to write it. Write subtraction vertically like that. Then let's look at the other side. I want to get XC. So XC is going to be found from taking BC and subtracting from BC, BX. And then I'll get this by subtraction. But you must give me two reasons. I need a reason why this is true, and I need a reason why this is true. It's not correct if you don't support your arguments. I need a reason for this, and I need a reason for this. Fortunately, these are both givens. AD congruent to BC is just this, written slightly differently. DX congruent to BX is this statement, written slightly differently. I need reasons for both of these. If you don't support your arguments, then your arguments aren't valid. They need to be fully supported. Now, I've shown the triangles are congruent. Pair of sides, another pair of sides, angle between them. I can see the side, angle, side pattern in here. So together, these three things tell me triangle BXA is congruent to triangle DXC by SAS. And then from that, we can conclude what we wanted to conclude. Angle B and angle D are corresponding parts. So I'll write corresponding parts. And we are done. Thank you.